Thank you. As Philip has mentioned, I'll be talking about the application of Sturmian theory to the formation of hydrogen molecules, which then served as a catalyst to the formation of the first stars in the universe. Before I begin, I'd like to acknowledge my support from the National Science Foundation, and to also acknowledge that my interest in this topic has arisen in large part due to long-time collaboration with Bala and Philip, and of course Alex and Hussein here at ITAMP. And I'd also like to take the opportunity to thank all of the members of ITAMP, Kate and Jim and Rick, Misha, and of course all the visitors through the years. It's been my privilege to interact with so many wonderful people, and in many cases collaborate with them as well. And Vasily, I should thank Vasily if he's here. Let's see.
I didn't do nothing.
And I'll thank you not to interrupt my talk. So I want to start with a slide that I use in my general education astronomy courses, and of course this just simply shows that the cosmology is now a very high precision science, and has many different phases or eras or epochs, whatever you want to call them. And of course we're down at the bottom of this picture, and we're looking back in time trying to figure out how it all came to be. And so the way that we do this, of course, is through astronomy, through the measurement of light, and whether that light is from stars or perhaps the background radiation. Tremendous advances in astronomy have led to tremendous advances in our understanding of how we got here. Now, you'll notice when you look up in the sky, it's dark, and that's because you're seeing a period of time before the first stars have actually formed. And so this is oftentimes called the cosmic dark ages, and it forms a bridge between the cosmic background and the formation of the first stars. And so, since there's no light coming from this period of time, our primary understanding of this period of time comes from mathematical models and simulations. And this is where atomic and molecular physics can really play an important role. And as Philip said in introductory remarks, the simulations are only as good as the data that is used in the simulations. And there's a lot going on in forming this bridge from the era of recombination to the, and I should say atomic recombination here, because I'll be talking about molecular recombination. But there's a lot going on here before the collapse of the halos into the first generation of stars. So a classic example of this dependency on atomic and molecular parameters was done by Turk and co-workers back in 2011. And they were simulating the formation of the population 3 stars, the first generation of stars. And they found if they kept everything in their simulations the same except for one single parameter, and that parameter was the three-body recombination rate for hydrogen molecules, they found a completely different result in their simulation. So for example, when the three-body recombination rate was small, there's 3 simulations that they ran. They were using rates that were published in the literature. So the smallest rate that they were using predicted a spherical collapse, which would tend to promote somewhat more massive population 3 stars. And then as they went to the next rate constant that was larger, they found more of a bar structure. And then when they used the largest three-body recombination rate that was available in the literature, they found a very spiral collapse. And these spiral collapses tend to cause a little more fragmentation, and the population 3 stars tend to be a little less massive. And I'll mention at the end, if I have time, why that's important. But the main thing is that it's not very often that you will see the results of macroscopic simulations be this sensitive to a single atomic and molecular parameter. So this is a great opportunity for an AMO theorist to see if there's any way that this controversy can be resolved or progress can be made.
Well, sorry.
Yes.
No guarantee if they will change other parameters, only other parameters. In other words,
there are no other changes. There's no other changes in their simulations. It is this single
parameter was sensitive.
There's a vast network of things going on in their simulations, and everything else is held constant. It is this single parameter that is changing that is causing this much difference in the result. Well, they may be, but I mean, we're trying to do things one step at a time, and this is the parameter that I'm studying. So this problem has a long history, and And the literature shows that typically the three-body recombination mechanisms are divided into one of three mechanisms. The top one is a direct mechanism, where M could be a spectator, could be another hydrogen atom, could be a helium atom, could be an H2 molecule, and it directly recombines to form H2. M just acts as the spectator. Or there could be a two-step mechanism, and if the two-step mechanism formed, and in both two-step mechanisms, one called the energy transfer mechanism, the other called the exchange mechanism, sometimes called the chaperone mechanism. In these mechanisms, there's an intermediate resonance state. So for the energy transfer mechanism, the resonance state is an HH resonance, and in the exchange mechanism, it would be an MH resonance, and then an exchange collision would cause the recombination. Now, in almost all the calculations that are available, the way that the calculations are performed is through classical trajectories. And by the way, I should mention that these two-step mechanisms often go by the name of orbiting resonance theory, and I'll be using that term. So, and that's because these resonances are due to the usual orbiting resonance, orbital angular momentum mechanism. And sometimes they're called RBC after Roberts, Bernstein, and Curtis, who proposed the mechanisms. But in almost all the calculations that are in the literature, these two-step mechanism results are added together as well as the direct. All three are added together to get the three-body recombination rate. And then in 1996, there was a very nice formal collision theory paper by Wee, Alavi, and Snyder. And they showed that if you were to include not just the orbiting resonances in these mechanisms, but you were to include the entire interacting continuum within each mechanism, okay, then they showed formally that all the rate coefficients should be identical. And with this in mind, I decided that Sturmians, which is something I had a lot of experience with working with Alex over the years, I thought, well, let's just use a Sturmian representation here, because you can get the resonances very nicely, and you can get all the rest of the interacting continuum. And because these are all supposed to be the same, I just figured I'll use the energy transfer mechanism, because that was the most convenient and easiest way to approach the dynamical problem. And I will be talking later at the end about the dynamical part of the calculation, which does formulate everything in the energy transfer mechanism. But I want to say formally at this stage that the Sturmian representation and the theory of Sturmians provides an independent verification formally without calculating anything of disequivalence. And I just want to show you that real quick. And the key to the demonstration is that the Sturmian theory is, of course, dynamical, but it also includes kinetics. And I'm not sure this is so well recognized, but what I want to show is that, and the reason I say it includes kinetics, is that if you look at this rate equation, where the square brackets represent concentration, the Kr is the recombination rate constant, the Kd is the inverse dissociation rate constant. The Sturmian representation provides a steady state solution to this rate equation, formally. And so what I mean is that the unbound states in the Sturmian representation, which I've labeled U, and the bound states in the Sturmian representation exactly satisfy detailed balance. And the sum over all, the unbound Sturmians provide a quadrature of the continuum, but because each of the unbound, the bound, and reverse rate coefficients exactly satisfy detailed balance, if you put in the equilibrium constants here, then you can use detailed balance to show that you get the Saha equation exactly. And you can get this using the unbound states being the interacting unbound states, which include the resonances as well as the non-resonant background. Or you can use these as unbound free states, in which case that would correspond to the direct mechanism. And the detailed balance argument still works exactly the same. Or you could formulate this in terms of the exchange mechanism. So if these rate coefficients were the exchange rate coefficients, and this, instead of being the H2 unbound state, it was the H with the M, and the unbound states of that exchange mechanism, the detailed balance argument, again, results in the Saha equation at LTE, local thermodynamic equilibrium. Now, the orbiting resonance theory is also a kinetic theory, but the orbiting resonance theory does not in any way give you back the correct statistical Saha equation at LTE. And so, of course, if your detailed balance isn't right, your kinetics can give you anything you want. And so the nice thing is that the detailed balance at LTE is built in to the Sturmian analysis. And this at least formally shows that the mechanisms at LTE are equivalent. So I also want to make another remark comparing Sturmian theory versus orbiting resonance theory. And it's because orbiting resonance theory is so widely used and still used today in the literature. So if you look at the expansion for the recombination rate constant, and you break it up into, if you want to call it the free part, they're not really free. They're still interacting. I'll just call it F just to give it a name and to indicate that they have very short lifetimes or very short time delays. And then those are essentially neglected in the orbiting resonance theory. And then you have the quasi-bound states, the interacting states that have substantial lifetimes. Those are the parts that are put in by the orbiting resonance theory, and of course those are the parts that are considered to be the most important in all the studies that are to date. Now, one additional, the Sturmian theory of course keeps them all, but the orbiting resonance theory does something else. If the quasi-bound lifetime is too large, they discard them. And this is a process called fall-off. And I'll explain what it means if you're not familiar with it. But I just want to mention there's a classic paper by Pack and Walker and Kendrick some years ago where they showed that this fall-off, which comes from discarding some of these long-lived quasi-bound states within the orbiting resonance theory, that it's incorrect. But they used a very complicated rate equation, numerical solution of a set of rate equations in order to demonstrate this. And I just want to show how the Sturmian theory can show you this conclusion very simply. And so the way to see it is this is the formal solution of the concentration, of the steady state concentration of the hydrogen molecules in a general unbound state. And so nothing's been calculated here. This is just a formal demonstration, but this is an exact solution of the time-dependent rate equation. And so if you look at the numerator, forget about this term in parentheses for a moment, because the orbiting resonance theory does just that. They effectively say this term in parentheses is 0. Then the argument goes, in the denominator, the orbiting resonance theory gets the same denominator. The tau u is the lifetime of the quasi-bound state. And if the quasi-bound state has a very large lifetime, or if the pressure or the concentration of M is very large, then you can see that this term here dominates the term, the unity term here. And so when you divide the equilibrium constant by this big lifetime contribution, they effectively would argue that the quasi-bound concentration goes to 0, which is why they remove it from the resonant state analysis of their theory. And the interesting thing is that if you look at the term in the numerator, as I say, the Pack, Walker, and Kendrick paper already has disqualified this fall-off, and the fall-off is not seen in experiments at any rate. But if you were to just look at this term in parentheses, this also comes out of the steady state solution of the concentration of these unbound H2 states. And if you put in for the concentrations of the bound levels with the U prime levels, you'll find that detailed balance can be used, and it shows that in fact this entire ratio is just the equilibrium constant. Right? And that is, I think, something of a new result, because even in the Pack, Walker, and Kendrick paper, they did this numerical analysis and found a small effect which was not identically the same as getting the rate constant here at LTE. So for a closed system, which would be an LTE, the steady state solution, is going to show no pressure dependence within the Sturmian theory. And I argue that this is required for the self-consistency of the kinetics. And so as long as it's an LTE problem, then it should not, the long-lived resonant states should be contained in the summation, but there's no lifetime dependence at all at LTE. So now, of course, cooling is a non-LTE process. And so here's a little cartoon. You have an atom or molecule with internal energy levels. You have a high-speed collision with another atom or molecule. And what happens is the internal energy levels of the atom or molecule get excited. And that slows the translational motion. And then when the internal energy de-excites, emitting a photon, if that photon escapes, then you have an efficient cooling mechanism, which is what is essentially going on in these early universe gravitational collapse models. And so this is a non-LTE process. So let's look at some of the gravitational collapse simulations to see where the various LTE, non-LTE boundaries lie. So there was an old paper by Flower and Harris. It's a nice paper in 2007. Almost all the gravitational collapse models have common features to this, so I'll just stick with this one. And what they find in their gravitational collapse model is that the dotted lines are LTE and the solid lines are the results of their simulations. And so what they find for the ground row vibrational state, at about 10 to the 4, NH is the number of hydrogen nuclei, and at about 10 to the 4 particles per cubic centimeter, the ground state is thermalized. And the more excited row vibrational levels, let's say V is equal to 3, J is equal to 6, in this plot, that thermalizes at around 10 to the 8 particles per cubic centimeter. And of course, it makes sense that the higher excited states would thermalize later because of the larger electric quadrupole transition rates. And it's also worth noting this 10 to the 8 is about the onset of where three-body recombination formation is believed to become important in these models. So let's look a little further at the. Sorry.
Do you know how they're determining the populations?
You know,
just collisions, or they include reactive channels, sinks, and sources?
You know, they've got a lot of things going on. They may have. I'm not sure they have everything, but they've got a lot of other things going on in their model. There's a large kinetic network that's included in the model, but I don't know the exact details off the top of my head. But again, all the gravitational collapse models do have a very large network of kinetics that are incorporated into their collapse models. And so here is the final approach to LTE for the entire system. That is the same thing as Saha equilibrium. And they show that it occurs at about 10 to the 13 or so particles per cubic centimeter. They also show the temperature is typically about 1,000. That's the generally accepted temperature range for this process. And since all the gravitational collapse models more or less have these common features, I'm inclined to believe that they're probably correct. However, I worry about it a little bit. And the reason I worry about it is because I've seen a lot of mistakes at LTE of detailed balancing. And so if there's mistakes in detailed balancing at LTE, then what I'm starting to look at is, you know, how do we do detailed balancing when you're not in LTE? And at any rate, that's what I want to talk about next, is how do we apply the detailed balance in the non-LTE limit and see if there's anything that can be learned from studying that.
Well, but sorry, do you have a balance really if it's not an equilibrium? You might.
Well, you get a steady state solution to the rate equation is what I'm referring to by the balance. So let me just show you what I mean exactly here in the next slide. So what I wanted to do was to model something that's a little closer to the gravitational collapse and include the exiting photons, because so essentially it's the same thing I showed before, except I'm now including radiative association in principle and also radiative dissociation. And now if I include them entirely, then you just get back to the Saha equation. It's a closed system and there's nothing new, nothing different. However, if you ignore the radiative dissociation, which is what essentially you have for efficient cooling because those photons are leaving, but you keep the radiative association, and then you take limits that the density is low, then you have a different non-LTE regime than you would have if the density is high. So it allows me to look, it gives me an additional knob to look at to take a different limit. And of course, if the density is high, C is just any neighboring atom. If the density of collisions is high, then the three-body recombination terms here are going to dominate any radiative terms here, and you have to get back to the Saha equation. And you do. But what happens in the more general case, you can write it as something, the steady-state solution, to answer your question, looks just like the Saha equation, except that you have this coefficient x, which needs to be evaluated. That x I can write in terms of some matrices, which I'll define in just a moment. But the main thing that in formulating this analysis is that, and making sure that it's right, is that it certainly has to give back the LTE limit when the density C is large. So that's the first thing. And so let me just mention what these matrices are. These are bound-bound matrices, matrix that needs to be inverted. There's a bound-unbound matrix that needs to be calculated, and there's an unbound-unbound matrix that needs to be calculated and inverted. And here are those matrices for a particular mechanism. Now I want to mention that at LTE, the different mechanisms give you the same three-body recombination rate. But at non-LTE, you get a pathway dependence. And so it depends on the kinetics that you put into your model when you're not at LTE. So this result here, which I believe is new, is for the EET mechanism, the energy transfer mechanism. There's another one which is a bit, it looks similar, but for the exchange you get something that looks a little more complicated, but it's in principle, you can write it down just like this. And it includes resonance lifetimes, the orbiting resonances. It includes the radiative lifetimes. These are the widths for the radiative process. And these matrices are not symmetric because of the fact that it's an open system and energy is leaving in the form of photons. So this, of course, requires a numerical solution. And I just want to mention, however, that you've got rate coefficients, you've got lifetimes for the orbiting resonances, you have the radiative lifetimes, you have all these things that are atomic and molecular parameters that go into this analysis. And in the end, of course, you've got all kinds of other things that could give pathway dependence. So this is not really a final solution in any way, shape, or form, because it only includes one single pathway. But I wanted to go through this model in order to try to understand, in a larger sense, what would need to be done for these simulations. So I also wanted, because the equations were somewhat complicated, I wanted to make sure that I haven't made a mistake. So I look at some limits, and first and foremost, I found when I invert these, I calculate these matrices, invert them and so forth, and I can find that, of course, I do get the Saha limit. And so that was, of course, the first thing that I checked. Then I took the limit that the density C is small, and in order to make it even more simple and transparent, I assumed that the orbiting resonance lifetimes also were small. And then you get something that's also very physical. What you see is you get a recombination numerator, which is due to the radiative association process. And then you get a denominator, which is the dissociation term, and it's all coming from the ground state. So B1 is the lowest bound state, or the ground state. And so all the dissociation here, when the limit C goes to 0, is coming from the ground state. So this is a physical limit that made sense to me. And so I think it at least argues that two limits of the complicated model at least tend to give me sensible results. Then in general, you want to solve this equation for this coefficient x, and then I would claim that that would give you the steady state solution of the rate equation. Now, in practice, these gravitational collapse simulations are extremely complicated. They have a vast network of reactions and so forth, and it's not going to be practical to carry detailed information about every unbound state. But you can, in principle, carry information about the quasi-bound states that have significant lifetime. And the Sturmian theory provides a self-consistent quantum theory, kinetic theory of how to do this. And as I say, I've not seen in any of these simulations any account of the resonances in a self-consistent way. As I mentioned before, the orbiting resonance theory is an inconsistent kinetic theory. It doesn't satisfy proper detailed balancing, and it can really predict almost anything, and it has. So to do it with a full, self-consistent approach, you of course need to calculate rate coefficients. You need to calculate lifetimes. You need to calculate a whole lot of atomic and molecular data, some of which I've done, some of which I haven't done. There's a lot of effort being underway to try to do better. Let me start with the orbiting resonances. David Schwenke had already published a table some years ago of all the orbiting resonances and their lifetimes. The Sturmian theory can reproduce them very nicely. I just want to mention that in these tables, these are all the known orbiting resonances for hydrogen molecules, or for H2, I should say. And the stars here represent what had been done in the classical trajectory calculations in most of the literature that I have seen. These are the so-called RBC states, and these are what people had in the past said are the important resonances that need to be included. But you see there's a whole bunch more, and I put some boxes around ones that turned out to be making a significant contribution to the overall recombination rate. And then I also wanted to point out, because there was, in the Pack, Walker, and Kendrick paper, which is a very important paper, at least to me it was very important. I learned an awful lot in studying that paper. One thing that they struggled with trying to include these broad widths and these interacting unbound states in the ET mechanism, the energy transfer mechanism. They even made the claim that it was impossible in a practical way to do this, because the way that they were trying to include these was to use L2 states that were truncating node by node, and they didn't seem to be able to find any good convergent way to include these within the ET mechanism. So they did a roundabout. They calculated the broad above barrier resonances and the unbound states using a scattering approach, and and then they put it in a separate calculation. I just want to mention that the Sturmian formulation treats all of these the same, and it does provide a convergent way of doing it within the energy transfer mechanism. So since I'm running a little low on time, I'm not going to say a whole lot about some standard stuff here. This is three-body collisions. You have the center of mass frame. Here's the H2 subsystem where we expand the basis and Sturmians. Then you have a dynamical formulation. Ideally, you'd like to use a coupled channel formulation. This is, of course, valid at all energies, but it's very expensive to compute, particularly for three-body recombination problems. The next best thing is a coupled states or centrifugal sudden approximation. I was able to do this for inert colliders like helium. But it does not work for, at least as it's, at the moment, it doesn't work for reactive colliders like hydrogen. So in the hydrogen calculations, the best I could do up to the present time is an energy sudden approximation. But because we're at high temperatures, there's some reason to believe that it's a meaningful calculation. So let me just mention that there is, in the chemistry community, there's an awful lot of study of negative imaginary potentials. And so there's a lot of things that are in common with the dynamical formulation that I'm using with the formulations that use imaginary potentials. Both of them use a single arrangement dynamical formulation, which is consistent with the energy transfer mechanism. In the case of Sturmian approach, the square integrability of the basis functions allows the other arrangements to be decoupled. However, you do get very slow convergence when using a diabatic formulation consisting of asymptotic row vibrational states. You can use this diabatic formulation for the energy sudden or IOS for any type of collider, and you can get a converged result. And you can use it for inert colliders if the coupled states, or in principle the coupled channel if it's a helium inert collider. However, full dimensional dynamics, coupled channel and coupled states generally require the use of a local adiabatic set of basis sets. I have not implemented this. But I should mention that this is standard procedure for negative imaginary potential calculations. And so there's a roadmap for what to do next. And so this roadmap is what I hopefully will follow in the years to come in trying to implement the Sturmians with the coupled channel. Here is just some quick results in the interest of time. I don't want to say too much, but you see there's the orbiting resonance contribution. You see the red curve here is an above barrier resonance, broad above barrier resonance. These dashed and solid curves are the discretized Sturmian background. And you can see even here it goes up to 25 discretized vibrational levels. And you can see there's even more. I think I went up to 50 in the calculations before you started to see a completely negligible contribution. And this was for H2. I also found that you needed to go to very high rotational levels. And in fact, I had to go up to 30 or 40 or so. 30 is almost converged. That's the dotted line here. At first, it looks like there's great agreement with an experiment, but that's completely accidental. And you can see that because there's no agreement over here, and there's this minimum that is almost certainly wrong. But the reason for showing it is that, well, first I wanted to show that 20 was not enough. And I had previously done some coupled states calculations with J max equal to 20. It starts to get expensive, so I stopped. The nice thing about the coupled states calculations is you can get the right shape in agreement with the experiment. It overestimates the experimental result, and in fact it would even be greater than this blue because the dash curve says you should go up to 30, and I only truncated it at 20. So the actual coupled state results are even going to be higher, although it does get the shape right. The disagreement is coming almost certainly from the potential energy. surface. The MR potential is very good when the stretching of the H2 bond is not too large, but it's very bad when the H2 stretching gets to be too large, which is exactly the problem that I'm looking at. So that is the problem. It would be great if somebody would calculate a helium H2 potential with a large stretching of H2, but nobody's ever done that. Now, the one thing that is interesting is that the IOS and the coupled states for Jmax equal to 20 give essentially perfect agreement above 600 Kelvin. That was one of the reasons that I claimed that the IOS, or the energy sudden approximation, is somewhat meaningful. And so above 600, 1,000 is really where the gravitational collapse simulations are needed. And so the red curve is my calculation. These are the three other calculations that were used in the Turk et al. Simulations that I showed at the beginning. And you can see that they vary, these three, the blue, the dotted, and the green, vary by about a factor of 100. And they're all, interestingly enough, all these three, the Paula, Abel, and Flower, they are all semi-empirical results that were based on experiments in this dark curve. These were experiments of Jacobs. And all three of these curves, which differ by 100, were basically built from these measurements using different interpretations of detailed balance and then extrapolation. And so two things. One, it's not that hard to get the detailed balance right. The Sturmian gives a transparent way of seeing that. You don't even need the Sturmians to see that, but that was one thing that was a byproduct of my calculations. And I'm within a factor of 2 of the experiments here. The other thing is that these extrapolations, my calculations find a much flatter dependence than these extrapolations. And so I just want to point out the limitations of my calculations. I've used an energy sudden approximation